Okay, so ladies and gentlemen, thank you for turning up again. I can see there's a few familiar faces. And when I say faces, I mean there's a few familiar names in the attendee list or attendee window as people still join. Today we're going to be talking about highly accelerated live testing, HALT, and that was on the request of one of our listeners or attendees or whatever we call people who turn up to webinars, because you're not just listeners, you're watchers as well. They wanted to know a little bit more about HALT, or highly accelerated live testing, after we talked about accelerated live testing in the previous webinar. And despite the fact they HALT and ALT, HALT has H at the start of that acronym and ALT does not, they are quite different. But as per usual, they all are part of the same arsenal of tools we have to create something that's reliable, i.e. something that does not explode, crash, just blow up, or do anything that we don't want it to do. When it comes to reliability, we need to be aware that measuring reliability can be important, or when we say measuring, that can be also interpreted as analyzing reliability, trying to quantify or work out the probability that something's still working at a particular point in time. But none of that is nearly as important as designing something that is reliable. If we are all about measuring without actually doing things that improve or enhance reliability and robustness, and all we're doing is admiring a problem. And the way we design reliability into a product is with a reliability mindset, not a flow chart that is several pages long, or not in a myriad of tests. It's all about how we go about enabling and empowering our employees, our workforce, our supply chain network, all those people, how we empower them and encourage them to use this reliability mindset. So let's use the example system I tend to use a lot in these conversations, which is the smart lock. A wonderful example of combinations of all sorts of cool technologies, including traditional mechanical lock technology and wonderful new smart functionality. Now, if we are at the start of our journey when it comes to creating a smart lock, let's just say we're a small startup company who wants to create a smart lock, we actually have a pretty good idea of what our smart lock's going to look like. Here you can see we have a pretty robust, consistent configuration that we can put together. We know that the smart lock's going to have around 16 different types of components. We know what's going to be entailed. It's up to us to work out how to put these components together to create an industry-leading smart lock that's going to wow customers and users alike. So before we even design something, whether you care to admit it or not, you actually have a really good idea of what it is you're designing. We rarely go into a design process. We have no idea if we're going to use batteries or resistors or handles. We have a pretty good handle, so to speak, of what it is we are going to be designing. Now, if we zoom in on a particular part of our smart lock, in this case, it's perhaps the most important part, it's the electric motor that turns the gear set to open or lock and unlock the lock. And of course, that electric motor is connected to the printable circuit board via cables in order to essentially give it the commands and controls to do what it needs to do. And if we just take the time before we even start designing our system or our smart lock to think about the effect that door slams have on these solder joints, this is, let's just say, a bit of revision for my regular attendees, but hopefully for those who are new, you really are starting to pick up what I'm putting down. And if we think about the effects that door slams have on solder joints, and solder joints aren't particularly structural, their main aim is to be essentially metals or alloys with low melting temperatures that we can easily manipulate to ensure we have good electrical conductivity between two different elements. But if we're going to have this smart lock installed in the door, which is slammed, then we need to think about these wonderful corrective actions you can see on the screen here. These are examples of what happens when we sit down, pause, and before we rush to design something that can work, think about what might go wrong. And you can see these wonderful corrective actions are very simple, they're very fast, and they're essentially free. if you include them in your first design. So this is where reliability starts to happen. You can also see the corrective actions don't just include design changes. 2 of those corrective actions are all about tests and inspections, which is one of the things that a lot of people complain about when it comes to testing for reliability. What do we test? Well, you tell me. If you start your design process with that reliability mindset and you're constantly updating, revising, and tackling the vital few weak points, you will have automatically written your test plan without even knowing it, just by understanding that you need to have that mindset every step of the way. And it's not overwhelming. It sounds overwhelming for people who have never done it before, but the whole idea behind reliability engineering is to find really amazingly useful techniques and activities to get to these corrective actions here before we invest too much time and money into designing the wrong thing. But let's just say we've got to this point, and even though these are some wonderful corrective actions we can think of that will eliminate or at least mitigate the damage we expect the solder joints to experience during door slamming actions, if we look at the PCB itself, the printable circuit board, we might also conclude that, hey, the door slams in a smart lock door slams of the door within which a smart lock is installed, it might actually have all sorts of awful effects on our PCB as well. And this happens routinely where we forget to understand the electric components or electronic components soldered to a PCB are also held to the PCB using solder, I should say. The PCB itself can crack, it can flex, can do all sorts of different things. The problem is we can't look at this PCB with our human eyes and walk away with a list of things we need to do to improve its robustness and reliability in the event of door slams. And that's where highly accelerated live testing can come into play. So just a quick show of hands. Who has heard of HALT? Can I just see a suitable emoji hand raising effort? People who have heard of HALT. So I can see the numbers are rapidly increasing. We're up to 17 hands, 18, so around about 20. So the majority of us have heard of HALT. Okay, so let's take those hands down. Of those people who have heard of HALT, who thinks they have a pretty good handle of what HALT is principally trying to do, or how you go about actually making a HALT happen? Okay, we can see up to about 6, 8, 9, 10 hands. Okay, so while the majority of us have heard of HALT, which means that some of us obviously are hearing about HALT for the first time, a minority of us feel pretty comfortable about what HALT does in principle. Well, the idea behind HALT, for example, is that we can quickly subject this PCB to special type of testing. And in this special type of testing, we within a matter of minutes, perhaps hours, we found that this capacitor right at the back broke free from our circuit board. Now, what that might mean to us is that, hey, this way this capacitor is connected to the circuit board, this PCB, is a weak point of the design. And it's very hard to, again, to visualize which parts of the circuit board are going to experience the most stress, because a lot of the time it's down to harmonics and vibrations. And for whatever reason, circuit boards, and it's all about where you mount the circuit board to the chassis, how force is transmitted to the circuit board, holes in the circuit board where wires are stuck through, the masses of the components attached to the circuit board, so on and so forth. It really is quite hard to know with absolute certainty which part of the circuit board is going to experience the most violent shock forces when the door is shut. And HALT is one way of perhaps answering that question really easily for us. And so that means that after we have found that this capacitor easily breaks free from our PCB when exposed to some stresses, we now have an additional corrective action, number 7, which is to install additional rubber mounts to isolate the capacitor from vibration and shock forces. Now, again, This corrective action, if it's embedded in our very early design, it does involve a little bit more cost, obviously, because now we have a few more components that we otherwise would have had. But in practice, if you identify this need early in the design process or the production process, it is exceptionally cheap to incorporate. And that's what we're trying to do. So what is HALT? We just said that HALT is essentially an approach where we were able to take that PCB, and that might be a prototype component. We might just ask our third-party manufacturer to send us a very early prototype so we can subject it to HALT to understand what's going well, what's not going well. But what does HALT actually mean? Well, let's look at a thing called a HALT test chamber. This is Hallmark Typhoon 4.0. And these test chambers are HALT and HASS test chambers, to be fair, and they're very expensive. And the reason they're very expensive is because they can do all sorts of really incredible things. So for example, you can put a product or a device inside this chamber and have the chamber rapidly increase temperature to up to 200 degrees Celsius and rapidly decrease temperature to minus 100 degrees Celsius. And how do we do that? Well, in the ceiling or the roof of this test chamber, there is very, very high power resistor load banks, which are essentially one big massive electronic radiator, so to speak, which allows an incredible amount of heat to be generated very, very quickly. And the air is circulated over those resistor elements to very, very quickly increase the temperature within the chamber to, in this case, up to 200 degrees Celsius. And when it comes to chilling the HALT test chamber, there usually is a supply of liquid nitrogen, which is then piped into the ceiling of the HALT test chamber. It then goes through isothermic expansion, isenthalpic expansion, like in just exactly the same way a refrigerant does, which then rapidly chills the air going over it so we can get down to extraordinarily low temperatures. And then there's a table, which is essentially a big, usually metal tabletop in the chamber itself, and it has lots of bolt holes that you can use to secure things to. And in this case, for this particular chamber, it can hold things up to about 600 pounds, which is obviously quite substantial. And that reason why we have this table and a table capacity is because beneath that table is a bunch of motors and springs and things like that to induce what we call 6 degrees of freedom vibration. Now, a degree of freedom is essentially, in this context, a way our table can move. So moving back and forth is 1 degree in freedom. Moving left and right, another degree of freedom. Moving up and down is our 3rd degree of freedom. But then there's also rotation. So pitching from essentially left to right, 4th degree of freedom. Using aircraft terminology, that's 5th degree of freedom. And what's the last one I'm looking for? Maybe attitude, I don't know. So using those analogies, I've run out of the right analogy. If I was paid more attention in pilot school, I would be able to nail this. But essentially, you have 3 degrees of freedom, which all about displacement, and another 3 degrees of freedom, and which are all about rotation. And the answer to your question, Robert, is no. Hallmark does not give me advertising fees. I'm just saying what this thing can do, and there's lots of other suppliers out there which create HALT test chambers which can do the same thing, and each one has their own strengths and weaknesses, and I'm certainly not going to advocate for one over the other today. But the main thing about this vibration is that it has to be random. It's very hard to do that, and that's where a lot of the money is sunk in creating these test chambers. Because when we say random, we want to have lots of different what we call excitation frequencies. And so if it's genuinely random, we essentially have all these vibrations at a huge range of frequencies, which is very important because different failure mechanisms and failure mode are all about certain excitation frequencies. So perhaps a capacitor is going to fly off at 10 hertz, but not 100 hertz because the harmonics of the PCB is not going to allow it to happen. Perhaps a resistor is going to fly off at 50 hertz of vibration, but not 10 hertz. And so the random nature of vibration is very important to excite as many failure mechanisms as possible. So let's see a HALT test chamber in action. So in this case, this is a video from Qualmark. And again, there is no advertising fees. And you're seeing a technician put a product into this chamber and sitting down at a computer which controls what the machine's about to do. And that machine, that chamber, is going to control the temperature, control the vibrations. You can see the cold air coming in. And you can also have, this is a test where it's fairly low in terms of the temperature extreme that you can potentially create. And you often have as aluminium or aluminum tubes, the similar tubes you see at the back ends of closed dryers, which duct the hot air to the outside of the house. Take this chilled and hot air and control it so that it goes over the component in question. Now, as a rule, we don't do HALT testing on entire laptops the way this lady is suggesting we do. As a rule, we don't do that. This is just a promotional video to essentially show what's going to happen. What we're more likely to do is take a prospective or prototype component like this PCB and subject it to essentially torture in our HALT test chamber. And you can see at this slow motion video just how violent that vibration can be when we look at it from the perspective of a component. And now it's slowed down even more. And if you pay attention to that capacitor on the left, which has this really nasty looking lean, with all the vibration, all the forces, all the bending moments associated with what is a fairly large component moving back and forth, you can see that at 50 G RMS, and we'll come back to that metric in a bit, our capacitor comes flying off. And so this might represent the first thing that breaks on our PCB while we're undergoing testing. And that might mean that in the future, or moving on from this test, we might conclude or be confident this is actually the weakest part of our design or our PCB design. So we know that we can do something to eliminate this particular capacitor flying off, then we'll be able to improve reliability by a long way, because this is the weakest part of our prototype. What we can't do as a result of this test is work out by how much we improve reliability. So let's dive down into these stresses and other things we use to torture our products and components. So if this horizontal axis represents time, and time in this case, our PCB is going to be subjected to HALT testing, we often start with what we call a cold thermal stress step test. And what that means is that we take our components, and Carl, to see your question is, will a copy of the presentation slides be available to the participants? And Carl, no, they will not. Instead, you will have a workbook, which is in the chat window as well. I don't think we're in the business of, in the practice of providing certificates yet, Carl. I'll let Fred answer that. But at this stage, I don't think you get a certificate. Correct me if I'm wrong. So let's go back to the screen where we're looking at how temperature is decreasing essentially by these little steps. As a rule, we control this step decrease, and we'll cover off why later. Now, at this point in time, when it gets to a certain temperature below 0 degrees Celsius, our PCB is going to stop working. And that means we need to actually test our PCB while our thing's being tested under HALT. We need to have some sort of test rig or wires connected to our PCB, running to an external test bed or a computer to essentially test the functionality of this PCB. So as soon as it stops working, we can have some device outside of the chamber say, hey, as of right now, our PCB is not working anymore. Now, let's just say if we were to remove that stress, it then starts working again. We call this our lower operating limit. Now, questions just come through. Why do we do this at the component level, not the system level? I will get back to that answer because it's a question, I should say, because it's a very good question, and it will become more evidence, hopefully, throughout the rest of this webinar. So I'm not going to ignore you. I'm just going to delay my response. So now we have what we call the lower operating limit, which is going to be a temperature reading. Maybe it's minus 50 degrees Celsius, minus 60, but that becomes our lower operating limit. Now, what we do is we keep testing. We keep testing. In this case, we are usually, in most HALT test scenarios, we're going down by steps of 10 degrees Celsius. So we keep going down these steps of 10 degrees Celsius until we experience a failure. And in this case, let's just say a resistor joint cracks. Now, the problem with this is that no matter if it doesn't matter if we increase the temperature again, it's still not going to magically repair itself. So what we do is we conduct root cause analysis on this resistor joint, and we found out that it failed because the test rig identified that our PCB broken and was now in a failed state. We then take the PCB out, visual inspection. Okay, so that resistor joint failed. We do basic or preliminary root cause analysis. Maybe we can come up with some corrective actions at the very start, or maybe we need to subject it to some more rigorous RCA later on, and we might work out it's a faulty solder joint or poor circuit design, or we might need to use a surface mount resistor instead. But the point is, we're all about speed when it comes to HALT. We want to quickly then patch up or fix the PCB. We might add some more solder or somehow mechanically secure that solder joint to the PCB. And then that allows us to keep testing it. But before we keep testing it, we then make note of the temperature at which that first failure, that first part that broke, occurred. And that becomes what we call the lower destruct limit. And so we keep testing, and we would expect to see more failures after that as the temperature gets even lower. And there'll come a point where we say, you know what, we're done. If we keep going, if we keep getting too cold, the actual state of the PCB is going to change. It's going to, some of the solder in particular actually changes its composition. For people who know what I'm talking about, the term eutectic might be involved here. But that essentially what our solder becomes is no longer solder that we're going to experience in normal operating conditions. We have a fundamental change in state. So that might mean we get to a certain temperature and we stop. The next part of the test might be going the other way, where we have a hot thermal stress step test, and then we go back to room temperature, and then we increase at 10 degrees Celsius at a time to find the upper operating limit and the upper destruct limits. And again, the operating limit is the point at which our device stops working. But if we were to reverse the stress, it would then start working again. And of course, we experience the first failure when we increase the temperature, we get our destruct limit. So Carl asks, this sounds like a very systematic and methodical process of analysis. Any thoughts about the need and importance for written documentation on the analysis? Of course, that's a good question. And of course, we really need to have great documentation. And sort of skip ahead a little bit, one of the many things that are open to us in terms of options for HALT testing is to get a third party to do it for us. In which case you have companies which only do HALT testing, and they have lots of fantastic HALT test chambers, which can cost many hundreds of thousands of dollars, which is why we often have a lot of third parties who do this. And they are, as a rule, pretty good at documentation. They're pretty good at noting what they observe. They're pretty good at recording everything. The reason being is that they have to forward that documentation back to you in a way that you can then use to improve your design. And so, yeah, of course, the written documentation on the analysis is very, very important, along with any observations. In some cases, just having a HALT technician say, hey, when it got to this temperature, I noticed this weird sound. I don't know what it meant, but it didn't sound healthy. That can be very, very useful. So, yeah, it is very important to have good written documentation to journal how you go. So this is phase 2 of a generic HALT test test profile. So we keep moving along, and we then, after these two serials, might then look at our upper and lower operating limits, the points beyond which our device stops working. And the third part of our test might be what we call a thermal cycling test, where essentially we rapidly change the temperatures that our poor old PCB is experiencing between the upper and lower operating limits. The reason why that's important is because due to thermal coefficients of expansion and contraction, the different components of our PCB will expand and contract at different rates. And that has been found to be I suppose, really mimic many of the sort of vibration-y stresses that our poor old PCB is going to experience in the real world. And so we have this wonderful reversal or cyclic stress caused by temperatures, which excite failure mechanisms in different ways. And of course, we're observing even more failures, and we conduct root cause analysis on each one to try and work out ways we can improve the design of our PCB. Now, once we've done that, before we move on, you'll notice that I have talked about steps, step increases and step decreases. You can see that for all these phases so far, we sort of dwell at specific temperatures. The reason why that's important is because if we zoom in at one of these dwell times, so to speak, you can see that the chamber temperature, or what we tell our HALT test chamber to do in terms of temperature profile, even though it looks like this, you can see a beautiful line which comes down to what we call a temperature set point, stays there perfectly before it moves off again. Our PCB temperature will always have a lag. It always takes a little bit of time for it to get as hot as the environment around it. And it also takes a little bit of time for it to start cooling down or heating up as the temperatures increase again. And so there's always going to be this lag, which means it's very important to have the right dwell time. And that means that because of that, we are able to ensure that every part of our PCB is going to essentially reach the same temperature. You can see another comment or question from Robert. Isn't this the thermal cycle more of a shock because of how rapidly the HALT chamber can ramp? And the answer is yes, it can be a shock. We want to be very careful about that, because when we say shock, it often means that, for example, one half of the circuit is down to minus 60 degrees, while the other half is still hovering around 0 degrees because it got blasted with the coldest bit of air first. So we want to be very careful about that. And that's why we see a lot of tubing, essentially direct airflow to components, because that sort of shock can be unrealistic in the real world, unless in your estimation, it actually is something that's going to reflect how the real world is going to torture our PCB. So yeah, I didn't say thermal shock, and perhaps I should have, but thermal shock is a very useful way of essentially exciting failure mechanisms we're likely to see. Is it typical to always use the LOL and UOL as a thermal cycling range limits? And the answer is, it depends. The problem is if you go too far beyond the UOL and the LOL, it sounds funny saying it, you risk just damaging your device through the mechanisms which essentially come into play when it gets too hot or too cold. So, yep, there's been plenty of limits that go between somewhere between the operating and damage limits, but and there are lots of different perspectives on that. And I'll sort of touch on the sort of tailoring approach, the experience you need to use when you come up with these profiles. So I'll come back to that in a little bit. But hopefully that dwell time is now, you can see why it's very important. We don't want to get, for example, down to minus 100 degrees Celsius for 5 nanoseconds, because that will not cool down the majority of our PCB. So we keep testing. Now, this time we're going to do something a little bit different. At room temperature, we're going to vibrate our PCB, step increases until it stops working. So now we have an operating limit. It's not an upper operating limit because this is for vibration, and vibration only goes in one direction. So we have the vibration operating limit. And then after that, before we move on, those steps are usually in the order of about 5 GRMS. Now, GRMS stands for gravity root mean square, or force of gravity root mean square. The root mean square is essentially a way of averaging metrics which have vibration or cyclic values to try and sort of characterize the typical amount of vibration going on. RMS is essentially one way of averaging that out. And it's always useful to relate everything back to the Earth's gravity, because that's a very universal form of some measure of force. And so we keep testing, and after we come to the point where our thing stops working, we can obviously keep testing until, in this case, our thing fails, in which case our capacitor, sorry, in this instance, our capacitor breaks free. And we come, again, with every failure, we do root cause analysis, and perhaps that's where we got this wonderful corrective action number 7, which involves incorporating rubber mounts to isolate the capacitor from vibration and shock forces. That is going to be installed on our next prototype. But the poor old prototype we're torturing, we just patch it back together and then keep testing. Oh, we're repeating this one again. I'll push the wrong button potentially. So that is now the destruct limit based on vibration, and we keep vibrating. And of course, we should get more failures until we reach the point where we say, you know what, we've done enough of vibration. And the last part of this profile is going to involve oscillating temperatures and step increases in vibrations. We're going to essentially destroy our poor old PCB to try and find as many failures as possible. And this is what our component's going to look like after we're done, and that's okay. We get to a point where we say, you know what, there's no point patching it together again. It is beyond repair. Now, a couple of questions are coming in. Can you explain the benefits of testing the PCB outside of the housing? Would this be unrealistic in the real world, since the housing or enclosure will provide a lot of protection potentially? The answer to that one, Eric, is there is no right or wrong answer. One of the reasons why we test PCBs by themselves is because, as a rule, if you are going to test it with the housing, it's going to cause a delay in the earliest available time to test. And if you can replicate the housing enough in a test rig or in a test bed, you can typically get the results of that HALT test a lot earlier for the PCB in particular. There's certainly been plenty of HALT tests that involve that PCB in the chamber itself. But there is no right or wrong answer. You just want to be very careful about imposing delays on the testing itself. If you can get away with testing the PCB by itself, and that gives you an extra couple, or gets results back a couple of months earlier, it's something you should really seriously consider. Robert asks, in the door example, a door slam is a mechanical shock, like a drop test. Couldn't a failure mode during vibration be different than mechanical shock? The answer is yes, it could. Now, we're not going to get a perfect correlation between testing in a HALT lab, or a HALT chamber, I should say, and the real world. And that's where a lot of people struggle with HALT conceptually, because a lot of us are trained to demand proof for everything. And if you're going to vibrate it in that particular way, prove to me that's it's going to be replicated in the real world. And we can never do that. This is all about experience. And those who've done HALT really well for a long time will tell you their experience shows that this is very, very useful. It replicates a lot of the real world failures very well. We'll touch on that later on. Because at the end of the day, the main point of destroying our poor old prototype is to get this wonderful second version of our PCB with some hopefully very simple corrective actions embedded within it. And that PCB, we can, if we want to, we can expose it to another round of HALT to try and find its weak points, and so on and so forth. William asks, how far can you push the prototype until you have made the corrective action changes to the point that the prototype is no longer representative of the product? Just to be clear, when we talk about the corrective actions, we are typically referring to the things you're going to put in the next generation of PCB. So you are never going to have a corrective action which is going to be implemented within an individual HALT profile. The reason why is because HALT takes a matter of hours in many cases. And so these are all essentially good ideas for the design team to come up with a better version. Now, the design team doesn't have to incorporate every single one of these good ideas because they actually might design the problem completely out of the system, but it's no longer an issue. And when you talk about the repairs themselves, I think you're talking about patching up the PCB so that it doesn't essentially reflect the original configuration, which is a fair point. And that is where you need to have really good HALT technicians and people who know how to run HALT, because it is a judgment call. If you need to have 16 meters of duct tape to hold this little PCB together, chances are, in the way you're suggesting, William, is that it's no longer going to experience the same vibration profiles. It essentially comes to a point where it looks like it does on the screen right now, where you essentially have to call time to the test and say, we are done. There's no point exploring this any further. And so we need to really understand how robust our prototype is, because if we just take it to a very high level of stress in the very start, we break everything straight away and we don't realize which ones are the first ones that need to be addressed. So hopefully that answers that question. Another question from Jorge: how long are the dwells typically? That is a subjective number. The reason being is because if your PCB is, for example, a motherboard for a computer, that maybe is a foot by a foot in terms of dimensions, that's going to take longer to heat up and cool down than this little PCB, which is going to be in a smart lock. However, the typical answer or typical dwell time is usually in the order of minutes. But again, a good HALT technician will be able to help you out with that particular conundrum. And so what we're left with this little profile I've just gone through is this range of stresses in terms of both thermal and vibration stresses, which we started off with a cold thermal stress test. Then we moved on to a hot thermal stress test. Then we had rapid thermal cycling, a vibration step test, and a combined thermal and vibration stress test. Now, this is, I want to say, the sort of prototypical HALT profile. And a lot of my microphone. Stand by. Sorry about this display of rank amateurism at my end. And a lot of this is again a very, let's call it stereotypical HALT profile. You often see a lot of documents say these are the steps you go through. And these steps are really, really good, especially for PCBs. Thanks, Fred. Notice that. HALT in progress. Well, my microphone didn't fail, so I'm going to terminate that serial right there. The reality is you need to use your own expert judgment in regards to your HALT profile. This is a really good idea in terms of helping you understand, for example, I have a baseline profile to start your HALT regime, but if you're not testing a PCB, or if your component is too big to put in a HALT chamber, or it's not temperature and vibration you're worried about, it might be fluid impact, or it might be voltage, then you need to come up with your own approach. And that can be intimidating, but again, a really useful HALT technician can be amazing in helping you come up with your profile. But this is the sort of profile you'll often see, let's just say HALT guidebooks around the world, this sort of 5-step approach. Now that means that we are able to walk away after our HALT on our first prototype with upper and lower destruct limits for temperature, upper and lower operating limits for temperature, and when it comes to vibration, destruct limits and operational limits or operating limits. And so these are numbers which we often see in those documents that we get after HALT test serial. The idea is that if we were to then subject our better version 2 to HALT, we would expect to see the destruct limits move out, the operating limits move out, and essentially our thing becomes more and more robust. Now, these operating limits and destruct limits should be well outside the, let's call it the use case or the use stress or the operational stresses our component's going to experience. And that's where a lot of pushback comes when it comes to HALT. We have people who say, well, of course it's going to fail. You pushed it beyond its limits against which it was designed for. The point is that we're not trying to prove if it's going to fail. We're trying to find out how it's going to fail. And that's why HALT is wonderful. And I'll echo the point Fred raised, that these two stresses, these temperature and vibration stresses, are only specific to most off-the-shelf HALT chambers. I think I mentioned voltage. I think I mentioned fluid impact, but you can see Fred has covered a number of different stresses that you need to think about when it comes to your HALT regime, because your component is not going to be a PCB in a smart lock. So I see a couple of questions coming through. Eric asks, can you talk to checking functionality? Sometimes certain components are not exercised during a simple boot up. Some circuits may need to be toggled. Any ideas about how to get a complete test for functionality without breaking the bank with test design? Yes, that's a really good question. If you have imagine testing a motherboard, for example, for a brand new computer in a HALT test chamber. And as you know, especially these gaming motherboards these days, there is so much functionality in there. It's borderline impossible to simply press a single button and simultaneously excite or check every level of functionality. It's a challenge that I don't have an easy answer for you, Eric. However, what you can do is, instead of testing for functionality, in many cases test for things like conductivity. Now, conductivity is not of itself a function, but you know that if your circuit board is not conducting from one corner to the other, you have a problem. It doesn't tell you what function you've lost, but it is a problem. And you need to, if you're using a third-party HALT test facility, you need to then have a negotiation with the technicians who are going to conduct the HALT in order to identify or come up with a regime for working out what failure looks like. And you may need to come up with a test rig. But again, many HALT labs are really, really good at being able to essentially have probes you insert on circuit boards that are able to measure conductivity, measure voltage drops and things like that, which then can be analogous to failure. And of course, all these examples I'm talking about are very PCB centric. PCBs are often, they're very widely used when it comes to HALT, or HALT is, sorry, I should say, one of them. You'll often see PCBs being used for being subjected to HALT more than other types of components. But again, without knowing what component you're talking about, we need to come up with ways to test for functionality, even if it's just through analogous metrics like conductivity. It is a huge problem that you need to be very, let's just say, strategic in overcoming. William asks, is there value to a waterfall approach to product development and HALT tests? That is, at some point we incorporate selected corrective actions, and do we run additional HALT? I mean, I'm quite cautious about endorsing a waterfall approach or a systems engineering V approach or a Scrum approach or Agile approach or whatever it is, because each different approach is actually really useful in terms of the philosophy they're trying to underpin. But the risk is that advocating for a specific approach then risks us having a bit of tunnel vision on things like HALT. Is it waterfall? Is it not? What I would suggest is that HALT allows individual design teams to act very independently. So if we have a design team for the printable circuit board, they can implement their own HALT approach independent of many other design elements of the smart lock, and that's very useful. So I don't know if that answers your question, but HALT can be used in many different ways, and I don't suggest that all the approaches to design, starting with waterfall, going through to Agile, there's a place for HALT if that technology allows it. And of course, there are times when HALT is not appropriate. There are certain things we don't need to do HALT, use HALT for. There's certain technologies which are so embryonic that HALT's just not a thing. It's just you need to work out the strengths and weaknesses for HALT as they apply to your component. Robert asks, so is HALT not a very useful tool for final assemblies? Is it better tool for PCBA only? And that's the same. I'm going to group your question, Robert, with the one that was asked earlier and come back to that one. I'm not going to blow you off. It's just hopefully I'll bring it all together a bit later on. So going back to our printable circuit board, which we've incorporated a number of wonderful corrective actions, which are highlighted in red, that have made a more reliable circuit board. But we don't know how much more reliable it is. We just know that it is. And we know that it is by a lot. That is, it has improved its reliability remarkably because we have essentially broken it in a number of ways and introduced corrective actions to address those ones. Now, again, you have just seen one profile of many potential HALT stress profiles. We do have this sort of stereotypical 5-step approach for HALT, which is perfect in many cases for many PCBs in a HALT test chamber where the only stresses are temperature and vibration. But even if you have a PCB, you might use a HALT test profile, which looks like this, where as opposed to doing those step stresses up front, we just simply start oscillating temperature in an increasing way, and we increase vibration. This one takes about 5 hours. And the problem with this one from many perspectives is that we have no operating limits, no destruct limits. And we sometimes crave those numbers because it allows us to visualize or quantify to an extent or identify that subsequent prototypes are becoming more and more robust. But a lot of organizations essentially use this rapid HALT profile because they're going to test a single prototype. They're going to get all the RCAs done for all these failures and just trust that the second prototype is going to be as reliable as they need it. And so that is another example of a HALT profile based on just temperature and vibration. But again, as Fred mentioned, as I've mentioned, you have to focus on how your thing fails. Current, voltage, fluid impact, humidity, static loads, all those things might be potential stresses that you need to incorporate for your product. And temperature and vibration are not a thing for your component. So use these, I suppose, standard profiles as guidance, and then move your way to a profile that's going to work for you. Then there's this thing called highly accelerated stress screening, and I'm going to be honest, HAS is something which I would have incorporated into this presentation or this webinar, or a couple of existing example HAS profiles. I had a couple of technological issues at my end, not HALT related, so to speak, but essentially, some of you might have heard of HAS, and sometimes people talk about HAS and HALT in the same sentence, and that's usually because HALT chambers and HAS chambers are exactly the same thing. What we're trying to do with HAS, highly accelerated stress screening, we're trying to improve design. We're trying to screen out substandard components and don't allow them to go into our final smart locks. And so there's some really useful rules of thumb, which usually involve cycling temperature and vibration to, in many cases, I think when it comes to vibration, it's usually about 50% of the destruct limits and temperatures up plus or minus 80% of the operating limits for the actual prototype. That you found these numbers during the HALT regimes themselves. The idea is that you want to accelerate or expose your component, your PCB, to stresses that are not going to of themselves cause damage, but will identify issues, manufacturing issues with your product or component that allows you to exclude it from being installed in your smart lock. So HALT and HAS are often talked about in the same breath, but you want to do HALT as early as possible. Not too early, because if you do it too early, then you're testing a prototype which is not representative. But if you don't want to do it too late, because then those corrective actions aren't fast, simple, and free anymore, they involve extensive redesign. HAS, on the other hand, even if it uses the same chamber, is done during manufacture. So they're very different, even though the acronyms are very similar and they use the same chamber. And also, don't confuse HALT with ALT, which in the latter is accelerated live testing. Accelerated live testing we covered in our previous webinar. For those who are brand new to this conversation, I'll give you a very brief overview. If we're trying to measure how long it's going to take for something to fail, we can create a chart like this. In the horizontal axis, you can see temperatures, and you can, in the vertical axis, you can see a logarithmic scale in terms of characteristic life. And this chart is scaled in a very unique way, which just so happens to help us understand by how much we accelerate a chemical reaction when we increase temperature. And that scale in particular means that if our thing is failing, in this case, our peroxide cured rubber is failing at elevated temperatures, and that failure mechanism is based on the chemical reaction, we should see a straight line on this particular weird chart. We call this an Arrhenius plot. The idea is that for example, we can compare two different sets of data to work out that at room temperature, or at least case 40 degrees Celsius, so a bit above room temperature, the peroxide cured rubber has a 1600-year characteristic life, while the sulfur cured rubber has a 170-year characteristic life. Now you can see here we're quantifying reliability. We're not trying to find the weak point. We have already gone through the perhaps HALT or analysis or a FMEA and identified that this particular component, which involves rubber, is going to fail through to rubber perishing or rubber degradation, which is a chemical reaction. And so you can see we actually have numbers associated with the reliability or the characteristic life of these two different rubber compounds. And the idea of accelerated life testing is we're able to get these numbers in a very short period of time, but not nearly as short as HALT. HALT can be done within hours. In this case, you still might be having to test these components for perhaps weeks in order to try and understand how long these things are typically going to last at use conditions. So HALT is always done before ALT if you're going to do it, because HALT helps you find or initially design out those weak points and helps you identify what the residual weak points are. And then once you have those residual weak points, you can work out what your dominant failure mechanism is and then study that failure mechanism. And if you need to measure reliability, then use an accelerated life test like this to come up with a number. But here, we're not testing every single failure mechanism. So it's only a very, very thin slice of how your thing might fail, which is, of course, okay, because this could be the dominant failure mechanism. So we usually do ALT later when we're trying to pick materials or understand things like warranty or mission reliability. So this is how we make reliability happen. We embed these corrective actions into our first design, and we do it in an iterative way. So if these red circles represent the vital few weak points, and we've just addressed, for example, the solder joints through corrective actions identified through FMEAs, then we might use HALT to target specific components in order to improve the design further. Then we have a really reliable product. So the two questions I said I would come back to, which essentially ask, why do we do it at component level as opposed to the entire system level? Because 9 times out of 10, by the time it comes to test the entire system, we can put the entire system together, it is too late. Or the corrective actions are expensive enough that you can only do a smaller number of them. So the idea is to conduct HALT as early as possible. And yes, that can be at the component level to move those HALT serials towards the start of the production process. So you can incorporate those wonderful corrective actions as fastly, as cheaply, and as efficiently as possible. If you wait till every single team has come up with their own design and it's been able to be manufactured and prototyped and all put together, you are by definition doing HALT later on. So hopefully that addresses those questions. But from a physical perspective or a physics perspective, there's no reason why you can't do HALT testing in the entire system. Just means from a budgetary and schedule perspective, by the time you do that, your scope to incorporate corrective actions has diminished. Robert says that we always did HALT on at least 4 units to help differentiate workmanship versus design issues. If all 4 units fail for the same mode or mechanism, then we can conclude it is a design issue. Can I comment? The answer is yes, I can comment, because there is an inherent truth to what you're saying. We just need to be careful to conclude with absolute certainty. For example, if all 4 units fail for the same mode or mechanism, it might be evidence to suggest that it is a design issue. However, it could be a manufacturing issue which is consistent across all 4 units, especially if we're into prototyping. So without being able to say with absolute certainty that those sorts of failures are design issues, I do concur that there is a certain truth to what you're saying, that if they're all the same, it can suggest that we're looking at a design problem. But don't ever rule out a manufacturing issue, especially if you're dealing with prototypes. Yes, and William then points out that a good root cause should identify manufacturing versus design, which is fantastic. So, for example, if your solder joint failed due to contamination, that is a manufacturing issue. But if your solder joint failed because the thermal stresses are simply beyond what a normal solder joint can experience, then it's a design issue. But I like what we're doing here because we're starting to critically think, and that's the key takeaway, critically think. And once we do this, we now have a reliable product. So we need to start with our decision. A lot of people say, when do I do HALT? When shouldn't I do a HALT? HALT's not appropriate for many components or many systems. You need to work out what it is you're trying to do. And that comes down to tests that either improve reliability or measure reliability. So if you're about improving reliability, if that's what you need to do, then the focus is finding as many weak points of failure mechanisms as possible. If you have tons of data and that particular component is not going to be changed very much from previous components, perhaps you don't need to do HALT at all. All you need to do is be confident that you have the vital few. If you're not confident, then perhaps HALT can work for you. If you want to measure reliability, then you need to have an understanding what the vital few are, and then focus on things like alt testing to try and quantify that. Those tests that improve reliability are usually very fast and very cheap. Those tests that are all about measuring reliability are usually a lot longer and cost a lot more money. So those improved reliability tests will essentially give you, for lack of a better term, a vital few report, which tells the design engineers what the problems are, or manufacturing engineers, I should say. It's being very design-centric in my language, and that's my error. It can be that we have a manufacturing issue as well. At the other end of the scale, when we're trying to measure reliability, we tend to rely on data. When we use data, failure is a random process. So by definition, when we infer stuff from a bunch of random variables, we have uncertainty in our conclusion. If that uncertainty is too much, well, we might need to get more information to reduce our uncertainty, which means we get more data, and that costs more time and money. There's definitely a place for measuring reliability, but a lot of reliability engineers I see essentially confuse tests that measure reliability with tests that improve reliability. Improved reliability tests are all about design decision-making. How can I make my thing more reliable? Whereas measuring reliability tests are often more about business or regulatory decision-making. Are we there yet? Did we satisfy the contractual requirement? What should the warranty period be, et cetera, et cetera, et cetera. All those things can be very important. But if we jump straight to measuring reliability without doing anything to improve reliability, then all you do is admire a problem. And that's not good reliability engineering. So measuring reliability engineering can be important, but not as important as making or improving reliability. So last point, and I'm re-emphasizing a point: decisions, decisions, decisions. What are we trying to do? Are we trying to work out if what it is we have reliable enough? Oh, that went too quick. What's going to break? What do I need to do next? What is reliable enough? Based on understanding your decision, you will need to work out if HALT is the right approach for you. Now, what I'm not doing today is suggesting that HALT has to be used. Far from it. I am talking about HALT as if it's a wonderful activity, because it absolutely is. But like any design for reliability tool, you need to understand what it's going to do, how it can help you. And the first thing you need to do to work out if that's is going to help you is understand your decision. That said, hopefully those of you who are new to HALT have an appreciation of what HALT is, how fast it can be, how you can go about getting a third party to help you out. And the reason why having a good understanding of HALT, even if you're going to outsource it, is very important, is because you need to speak a common language with the HALT technician. And HALT technicians don't know your individual organization's needs as well as you do. So if you know that there are typically 5 steps to most stereotypical HALT profiles, and if you know that your component is likely going to have failure mechanisms that are going to be excited by things besides temperature and vibration, then you need to have a conversation with your third-party provider where you stand your ground. And you can't do that if you have no idea about HALT. So hopefully today has gone some way to helping you feel more comfortable having that hypothetical conversation. So I'm right on time. We answered a ton of questions. Apparently I answered 17 questions in the question and answer window. So I'm sure Fred stores his data meticulously somewhere, the same way Major League Baseball does. Now we have 18 questions. Williams wrote, have had good luck performing HALTs on products too large for a chamber using a truck, a washboard road, and potholes, and good accelerometers for a very low temperature commercial food freezer. Stress extremes for large products are lower. Thank you, William. That's fantastic. What I didn't do in this conversation today was actually come up with describe a really applicable real-world HALT profile, which doesn't involve a chamber. And I've been involved in plenty of them myself. So thank you for fixing that hole in my presentation on my webinar today, because great example of how you can do HALT testing by yourself. The faster you drive over that washboard road, the more vibrations and different vibrations you're going to experience on the thing in the back of that truck. Of course, won't be quite as scientific. You won't guarantee 6 degrees of random vibration, 6 degrees of freedom, but you're using your brain to try and work out how to accelerate the stresses that thing's going to experience. And if that thing is going to be a component in a truck, you know what? Actually probably is a really good representative test. HALT does not have to be exact and well calibrated. No, it does not. But what I would suggest is no matter what you do, try and incrementally increase the stresses so that you work out which thing failed first. What you don't want to do is do a HALT program where you have 40 failures, but you don't know which one occurred first, because the thing that occurred first is the weakest point. So that's not a challenging problem to overcome. But again, that's where we need to think creatively to come up with ideas to be able to work out which thing failed first to create that list of the vital few. Josh wrote, going back to the comments, I should say, about component versus system level. If we are designing a new product and the previous generation did not go through most reliability testing, is HALT an option to understand how the previous generation might fail and how it could compare to the next generation? Ideally, if you're talking about an incremental improvement on an already fielded component, ideally you would have access to field data, which in a way is as good as you can get when it comes to reliability concerns. I'm guessing, Josh, that you don't have that data, in which case that the actual reliability performance of this component might be invisible to you. So in that case, HALT is certainly an option to understand how the previous generation might fail in your new application. However, I try and search rather exhaustively for existing field or failure data, because that could actually be an even better source of information. But HALT is an option in that scenario, absolutely. Any more questions? I assume those hands from Maximilian and Ashwin are actually residual hands from the poll I did earlier today, unless that is representing a question you want to ask, in which case type away. William wrote, HALT planning can be coupled with risk assessment of the product to identify the most valuable profiles to explore first. Absolutely. We want to know which stresses are the ones that are going to excite failure mechanisms. And that is a term that reliability engineers use a lot, excite failure mechanisms. And reliability engineering is not often very exciting, but in this case, it is. When we use the term excite, it means it has that unique combination of external stimuli to make corrosion or fatigue or whatever it is raise its ugly head in your HALT test chamber and not in the field. So thank you for some really good input, William, because you raised some really good points. Kenneth asks, what approach would you suggest if HALT testing does not cause a failure, the failure occurs with our customers? Now, as a rule, HALT testing has failed if you don't get failures. So you are going to have to come up with a profile in which you generate failures. Now, if you do a HALT profile or run a HALT test and it doesn't fail, you have to go back to the drawing board in terms of those making those failures occur. And of course, I think you might also be referring to, say you do a HALT profile and you get 40 failures, but in the hands of a customer, you get an additional failure which you didn't observe during HALT. And that's obviously always an option because failure is a random process. So that happens more often than you'd think. But the idea is that we're never going to eliminate the probability of failure. The idea is that we want to eliminate the vast majority of failures by addressing the vital few. So if your HALT testing, so let's say identified 40 failure modes, and let's just say you identified corrective actions for all 40 and incorporated them in your new product or new model, then the fact that your customers are experiencing a different failure mechanism actually might validate that you have address those vital few weak points well, because now that you've addressed those vital few weak points, there's going to be a whole brand new set of vital few weak points. But the good thing about that new set is that they're going to be stronger than the original set of vital few weak points. So hopefully that touches on some points that might come close to answering the question. Maximilian asks, when your HALT testing fails, you did not pick the right... Okay, sorry, you were just repeating what I said, or sorry, emphasizing what I just said. Thank you for that. So yeah, if your HALT profile doesn't cause failures, you've got the wrong profile. If you are testing explosive products, exciting failure mechanisms has a very different meaning. Touche, William, concur. In fact, HALT testing has been done on a lot of things which might not necessarily relate to explosive testing, but things that need to withstand explosive or percussive forces. Armor for military vehicles is something which often gets exposed to very, very tailored HALT test profiles, as you can imagine. Any more questions from anyone?
Hey, Chris, I'm going to jump in on one of the thoughts that Maximilian brought up. I think he was reiterating what you're doing, but I've also seen products that are very, very robust. And for the variety of stresses that were of concern, it went to the limits of the chamber. You know, we can only go to 100 minus 100 degrees unless you live in Canada. So sometimes we're limited by, can we get there to a stress that actually excites a failure? And then other times, I always use the example on high temperature. You know, if you get to 200 degrees C and you used a lower temperature solder for some reason, that solder will melt. You've reached the physical limits of the materials you're using. Now, if the first failure you'll get is that solder melting, and it's well away from anywhere that you're going to see the product's exposure to temperature, you've reached the technology limit of your design, and it's fine. That's actually a good failure to have if that's your first one. And so, or it's a revelation that, we need to survive that temperature and we got the wrong solder in there. So it could go either way. But there are times when you don't get, the 40 failures in HALT, because one, you got a great design, or you've reached the limits of your ability to apply stress to it.
Thanks, Fred. Great points. And also add, not only can your solder melt, it might change its composition. It's an alloy. When it changes its composition, you can't see it. But when it gets hotter or colder, and there's going to be some people who know more about solder than I do on this conversation, it just turns into a different material, which again, as Fred points out, might not be going to experience in the real world. So I think, Fred, we're just saying there's no absolute rules for HALT. Does that be a fair?
Yeah, the best thing that, and
summary?
you covered it, Chris, is that it's the approach, is that you're intending to cause failures to occur. And the concept is that those failures, when you exercise HALT in like a stepwise fashion, typically then represent your weakest links. And those are that vital few that you talk about so much. And that's important information that we can actually do something about. The worst you can do is say, oh, here's a fixed profile, just run this and then hope for the best. No, you have to step back and think, what are the right stresses? What are the threats that this product's going to see? What do we need to know? What's our decisions? You really do need to spend the time up front to think through how you're going to design this. And there's plenty of them that are not done in a HALT chamber, despite what the HALT chamber manufacturers will tell you. So,
yep. It's a great tool though. You just need to know when to use it. But
that's right.
If the only tool you use is a hammer, then everything becomes a nail. You just want to be careful of just using the same tool over and over again. Any more questions? William wrote, William, you're busy today. Thank you. European lead-free solder will have a life limit and last temperature vibration tolerance, i.e. GM instrument experience over the years. So I think you're touching on what Fred's talking about, William, where essentially it has design limitations which are known, which need to be incorporated in the design, and essentially pushing that component beyond those limits during HALT will not give you a failure mode indicative of the real world. But again, yeah, it just sounds like you're using this thing called critical thought, William, which is fantastic. That's probably one of the main takeaways. You've seen an example HALT test profile. Take what that profile represents and apply it to your system. Don't just copy and paste. And no, we have not been sponsored by any HALT chamber manufacturers, as far as I'm aware, Fred. That might have changed during.
Nope, we don't do advertising, so nope.
Yeah. Cool. All right, ladies and gents, you have our contact details. You have my contact details. You should have access to the workbook right now, so you should have most of today's conversation, most of the information from today's conversation at your fingertips right now. If you have any further questions, please feel free to reach out. One of our contributors is a HALT. What do we call Kirk? HALT savant? HALT.
Well, he's done so many. Yeah, he's a HALT authority. He wrote the book on it, and he's done hundreds, if not thousands, of HALT processes. So yeah, he will set you straight if you're off on a wrong tangent.
So Kirk in particular is a really good resource, and I'm pretty certain he's like the rest of us and more than happy to share his experience that people will ask. But again, if you have any more questions for myself or Fred or anybody else, please reach out. And if there's anything we can do better, please let us know. But beyond that, thank you again for your time today.